Welcome to my tutorials on understanding limits. In this tutorial, we will be covering the basics of limits and how they are used in calculus. We will be using examples and visual aids to help make the material easy to understand. Limits. So let's move on. Why studying limits? Why studying limits? Limit is used in so many real-world applications. For instance, in physics, limits are used to describe the behavior of a system as certain variables approaches certain values. For instance, in the study of fluid mechanics, limits are used to predict how fluids behave as they flow through different types of pipes or around different types of obstacles. That is in fluid mechanics. In engineering, limits are used to determine the maximum load that a structure can support or the maximum speed at which a machine can operate. That is in engineering. So when we come to economics, limits are used to study how markets behaves, particularly as the supply and demand approach equilibrium. So when we come to the calculus that we are currently about to study, or we are currently studying, limits are the foundation for many other concepts such as derivatives and integrals, which have wide application in science and engineering. That is in the calculus that we are studying. In computer science, limits are used in analyzing algorithms and computational complexity. So when you come to statistics, which is also very important, limits are used there to understand how sample, means, variance, and other statistics converges to population parameters in large sample sizes. So this is some real-world application that you can use the knowledge of limits to apply over there. So let's come to the definition of limits. First, let's define what a limit is. A limit is a value that a function approaches as the input of that function approaches a certain value. In simple terms, we say that the limit of f of x is equal to L as x approaches a. And this is how we write it. That is, the limit of f of x is L as x approaches what? A. Provided we can make f of x as close to L as we want for all x values sufficiently close to a from both sides without actually letting x be a, right? Provided we can make the all x values close to a from both sides sufficiently close to a from both sides without actually making x to be equal to what? A. For example, we say that we have the function f of x, which is equal to 2x plus 3. The limit of this function as x approaches 4 would be 11. Would be what? 11. How did you do it? We have different ways of evaluating limits of a function, and one of them is an algebraic approach. But we have three different ways. We'll be talking about these types of or these ways of finding limits of a function in my subsequent videos. So the limits of the function f of x equal to 2x plus 3 as x approaches 4 is equal to 11. That means that as x gets closer and closer to 4, right, the value of the function gets closer and closer to 11. we just did some simple illustration or simple substitution, which is what? 2 times 4 plus 3, which is equal to what? 11. And this is an algebraic way of finding a limit, and we'll talk more about that in my subsequent videos. So let's look at this graph to aid in our understanding. This graph was picked from one of the calculus book called Bass Calculus, and you can go and refer to it to get more details from there. So based on the example provided, which is f of x equal to 2x plus 3, this is the graphical view of the function. So we can see that here is 2 and here is what? 6. That means 4 lies between here. It's 2 and then the 6. So that's from 2, 3, 4, 5, 6. So find a limit from both ends. That is from the left side of 4. As x, the value of x approaches 4, we can see that the function value, which is y, approaches a value called 11. Let's also come to the right of 4. You can also observe that as x, the value of x approaches 4 from the right, the function value, which is y, is also approaching what? 11. Therefore, the graph 2x plus 3 with x approaching 4 and the corresponding y value also approaching what? 11. It is important to note that a limit does not have to be equal the value at the point it approaches. In fact, a limit can be infinite or not exist at all. Let's take g of x, for instance. G of x equal to 1 over x, for instance. The limit as x approaches 0, the limit of this function 1 over x as x approaches 0 does not exist, because as x gets closer to 0, the value of the function becomes larger and larger without bounds. Let's take a visual look at this graph. We can also see that as x approaches 0 from the right, that is, this is the right, this is x axis and then the y axis. So as x values approaching 0, here is a 0. From the right, we can see that the function value, which is y, approaching infinity. We can also see that as x values, this is the x values from the left of 0, approaching 0, the function value, which is y, also approaches negative infinity. So this means that the graph of g of x equal to 1 over x with x approaching 0 and the corresponding y values becoming larger and larger without bounds means that the limit does not exist. So limits are used in calculus to help understand the behavior of a function and to find derivatives and integrals. Understanding these limits is crucial for understanding many important concepts in calculus, such as continuity and differentiability. You can find the limit of these functions using 3 main approaches, including the numerical approach, the graphical approach, and then the algebraic approach. So my subsequent videos will show you how to use these approaches in finding the limit of a function. That concludes our tutorials on understanding limits. I hope you have a better understanding of what limits are and how they are used in calculus. My next video will be showing you how to find the limit of a function with examples using the numerical approach. Thank you for watching.